A building is never at rest. From the moment the frame goes up, it is locked in a physical fight against gravity, wind, and time. On a professional job site, these structural principles function as legally binding obligations, moving structural stability from a design choice to a statutory requirement. That legal framework operates as a strict hierarchy. At the absolute top is the Building Act 2011. This is the ultimate statute in Western Australia, providing the legal mandate that a structure must be safe and compliant. Directly beneath the Act are the Building Regulations 2012. These define the exact legal pathways, certification requirements, and conditions necessary to actually obtain a permit. Forming the foundation of this pyramid are the Australian standards, documents like AS 1684 for timber framing and AS 1170 for wind actions. These provide the specific, engineered math that dictates how you must physically construct the building to meet the regulations above it. A structure's physical survival on site and your legal survival as a builder depend entirely on satisfying this regulatory hierarchy from the ground up. To satisfy those standards, we have to quantify what the building is fighting against. In engineering, a force is the action, a physical push or pull. A load is the resulting weight or pressure that the structure actually has to carry. Primary loads act on a house as invisible forces that never sleep. Every structure is designed to handle these by default. Notice the specific directionality. The dead load, the permanent weight of the materials, and the live load from occupants both push straight down. But wind load acts laterally, pressing against the walls and creating massive uplift on the roof. Then there are secondary loads. These are highly situational, depending entirely on the local environment, but ignoring them leads to identical structural failures. For example, building in Western Australia's reactive clay soils introduces severe settlement loads as the ground swells and shrinks. If you're pouring a basement, you must engineer for hydrostatic pressure, the crushing weight of groundwater pushing horizontally against the submerged concrete. A builder's very first responsibility is identifying and calculating the exact combination of these loads before a single trench is ever dug. Once you know the total load on the building, you have to manage how those massive forces interact at the micro level, specifically at the connections. Look at the top two panels. When forces act along a single flat surface, they are coplanar, like rafters on a ridge beam. When multiple forces meet at a single base point, like weight on a column, they are concurrent. Collinear forces act in a single straight line, like tension on a tie-down rod against wind uplift. Parallel forces act in the same direction without ever intersecting, which is exactly how a bolted shear plate distributes its load. Whenever these forces are applied to a horizontal beam, the material will physically bend. This movement is called deflection. This diagram shows a cantilever beam, fixed at only one end. Because the other end is entirely unsupported, the absolute maximum stress and downward movement occurs at that free tip. Contrast that with an overhanging beam, which sags in the middle while the tip droops. A fixed support beam, pinned at both ends, experiences a symmetrical curve, with the maximum deflection occurring exactly at mid-span. Deflection is an inescapable reality of physics. The goal of structural engineering is not to eliminate the bend entirely, but to predict it and restrict it within the strict allowances of the building code. To restrict that bending, simply increasing material volume is inefficient. Strength is dictated by geometric orientation. Every beam has a geometric center called the centroid or neutral axis. This is the exact midline where the crushing compression on the top of the beam and the stretching tension on the bottom meet and cancel each other out. This diagram shows the second moment of area, or inertia. Look at the left side. If you lay a standard 90 by 45 mm timber joist flat, it has a low moment of inertia, resulting in excessive mid-span sag. The mathematical formula for inertia divides the width times the depth cubed by 12. Because the depth value is cubed, it completely dominates the equation. Rotating that exact same piece of timber onto its edge makes it 4 times stiffer. A similar geometric principle applies to vertical columns. The radius of gyration measures how effectively a tall, slender column can resist bowing outward when heavy compression hits the top. Manipulating geometry, rather than simply buying thicker timber, is the ultimate secret to structural efficiency and cost control on site. When all these columns and beams are perfectly balanced, the building enters a state of equilibrium. The physics of keeping it stationary is called statics. This diagram shows the 3 non-negotiable mathematical conditions for a structure to remain at rest. The sum of all vertical forces, horizontal forces, and turning moments must each exactly equal 0. Turning moments are calculated by multiplying the applied force, here 8 kilonewtons, by its physical distance from the pivot point, 2.5 meters, resulting in a 20 kilonewton meter turning force. These theoretical equations translate into hard numbers on site. For example, a soil base with a bearing capacity of 100 kilopascals can safely support roughly 10 tons of load per square meter. To maintain that equilibrium, building materials must absorb 5 distinct physical stresses: tension, compression, shear, bending, and torsion. Materials map their resistance on a stress-strain curve. Initially, they operate in the elastic zone, bouncing back when the load is removed. But if they cross their specific yield point, they enter the plastic zone, suffering permanent deformation until they reach catastrophic fracture. In construction, there is no perfect building material. Great engineering relies on matching a specific material's yield point to the precise loads demanding equilibrium on your site. Zooming out to the macro level, wind currents create complex aerodynamics as they wrap around the building, effectively transforming the entire structure into a sail. Intense positive pressure hammers the windward side of the structure, while simultaneous negative suction on the leeward side tries to rip the roof entirely off the frame. This diagram introduces the building diaphragm. These rigid horizontal plates, like floor and ceiling systems, collect massive wind forces. Notice the unbroken load path. Wind hits the windward wall, transfers into the ceiling diaphragm, shears down bracing walls, into the floor, and dissipates into the soil. This diagram shows exactly what happens if that load path is severed. The building will suffer one of 4 structural failures: racking, where the walls lean, overturning, sliding off the foundation, or uplift. A fully connected, unbroken load path is the single physical lifeline preventing a structure from tearing itself apart in a storm. We physically combat the failure modes we've identified by installing wind bracing. It acts as the building's structural seatbelt, tensioned elements installed specifically to lock the frame in place. The geometry of that bracing dictates its utility. Cross bracing, forming a full X, provides the absolute maximum lateral efficiency. But designs like K-bracing and V-bracing are frequently used to maintain that strength while leaving necessary voids for doors and architectural windows. Perfect geometry still fails if the material itself is weak. That is why structural elements cannot rely on simple visual timber grading. They require precisely tested, machine-graded pine to guarantee their exact hazard and stress levels. Transferring all of these accumulated loads securely into the earth requires serious geotechnical anchoring. Look at this observation platform at the Gap in Albany. To achieve equilibrium against violent Southern Ocean winds, engineers had to drill 9 meters deep straight into the solid granite cliff, securing anchors that hold a 27-ton load capacity each. Whether bolting a cliffside platform, pouring a gravity retaining wall, or shoring up a deep excavation, the mathematical principles of statics and load transfer remain identical. A building is a living, working system under constant stress. Mastering the physics, respecting the strict legal regulations, and engineering a completely unbroken load path is the definitive difference between a structure that stands and one that fails.